So we have an increase in arc length as indicated with the purple color as we go from some beginning point X to some point at a distance along the x-axis, x plus dx. As I was saying last week with the differential, for the change in x, what would be your differential change in x? You can write dx, you can write delta x, you can write h. It's all the same thing. If you think of your math 170 and the definition of the derivative as a limit, I think the book and probably whoever was your teacher used h, and f of x plus h minus f of x over h, take the limit, and so on. However, for the differential change in y, dy, that would be, as we were doing last Friday, the distance from the green up to the blue. It's the distance to the tangent line, wherever that would be. And in this picture, then the dy, which is the red in there, is less than the delta y, which is the change to wherever the curve actually is. So if your curve is concave up where you place the tangent line, then the delta y would be greater, and if it were bending down at the point where you place your tangent line, then the dy would be greater. And they're only the same if your curve is a straight line or at occasional points where the line continued and the curve continued might happen to meet. So anyway, arc length is always increasing, as I've said here. So what we have then is that for small enough dx, then the ds, the differential arc length, measured along the tangent line, and the delta s, which is the actual tape measure arc length along the curve, will be approximately equal. You can see that they're different here, but if you come back toward the beginning and think of smaller and smaller dx choices, so say you're back about where my stick is, now it's pretty challenging to say that there's a difference that your eye would pick up between the length on the purple and the length on the blue. So that's the idea, that differential quantity, the difference between some quantity that you're trying to get a value for and the differential approximation to it will go to zero as your differential in x goes to zero. So it's in a limit sense then that we can use the differential triangle dx, dy, and ds as in the law of Pythagoras to represent the arc length. So law of Pythagoras then relates the green, red, and blue differentials. And so if you're thinking of s as a function of x, then you could also think of your differential quotient, which you remember from last week is always numerically equal to your derivative. So you could think of ds dx then, which would numerically be equal to s prime of x if the arc length is a function of x. So it would be square root of 1 plus dy dx squared. And again, your dy dx is numerically equal to f prime. So as numbers, you can get this equality. If your S, your arc length is a function of Y, then you can get the corresponding equality here, that your ds dy, or S prime of Y, square is 1 plus G prime of Y, quantity squared. If X is G of Y, and again, if dx dy is numerically equal to G prime. You remember my example last week, I held up the money, I had the 250s and the 100, said that was 50 gallons of gas. That was last week. I think you can get a little more this week. And the stock market and the oil companies and the oil workers in North Dakota are that much more unhappy as the time goes. So anyway, we have the ds dy formula here, and we have the ds dx formula. The other topic, if you notice on our schedule, we're doing both 6.3 and 6.4 sections today. And so the 6.4 idea goes right along with this. Suppose you want to take a curve and rotate the thing around the x-axis. If you do that, you create a surface called the surface of revolution. So to get the surface area, we take 2 pi times the radius from the center axis to the curve. So in this picture, it would be 2 pi times y, where y would be f of x. And then we don't just say dx for the width, which you see would be horizontal, and that's too different from the actual length of curve that you're rotating, which is the ds. So we take 2 pi times the radius from the center axis times the differential arc length, which is the same formula that we use here to get arc length. You see, if you took both sides here and multiplied by dx, then you have ds is this dx, and that's what this is. So this is 2 pi radius ds, where x is the variable. And so for rotating around the y-axis, in other words, if the center axis were vertical, then the radius would be a function of y, and this would be your differential of arc length in terms of y. So we will be, the homework problems that are on the board are using this formula or this one for arc length, and they're using this formula or this one for the surface area. And as always, what I'm doing now is some of the problems in the book, and as I think you understand, and as I said last week, you have your choice. You can do the problems as on this sheet that are in the book, write them out and turn them in, and I hope that I'll be collecting some homework from somebody at least. If you're doing it that way, fold your paper over like that, put your name and what section it is, and Math 175 on the outside. You can write on both sides of the paper. You can staple it or not. And you can use lined paper, plain paper, pink paper, green paper, whatever you want. Recycled paper, whatever. Otherwise, you can do the My Math Lab sections. So anyway, we did 6.3 number 1 last week, which you would remember seeing if you were here. So look at number 2, where y and before we do, I have a handout, which doesn't surprise you, I'm sure. So this is some more of the student package. You see again with student calculus 1. And if you want to draw graphs, you need the plots package in some situations, so I also brought it up. And then you can type in whatever text you want in Maple, which is one of the nice things about it. You can go from math and what the computer prints from the math commands into a mode where you're just typing text, all in the same program. So then problem 1, which we did last week, you see, first thing I did was to get Maple to draw the graph, which was the x squared plus 2 to the 3/2 power over 2. You see the curve, and then since you have the student package, you can simply type arc length and ask for the plot. If you do that, you look at the back, and you see that it gives you 3 graphs. So it's color coded. So for this to work well, you would need to have a color monitor, and of course, if you want and you can see, of course, that what I had was a color printer. It would still produce the pictures, even if you didn't have color, but it would be harder to tell which curve's which. So you see they give you a kind of little key there, that what's in the red is your graph, so that should look like the graph on the other page, on the back of the paper. And then what they're calling G, which is in the blue, is a graph of the square root of 1 plus the squared derivative. In other words, it would be the graph of this, the graph of the differential arc length in terms of x. And then the third one, which is in the light green, would be the integral of the second one, so it would be the actual arc length, the tape measure length as a function of x. And then if you want the actual arc length integral, you see I typed arc length and output equals integral, and then if you want the number, you type arc length and the formula and the limits on x, and you get 12. And then I'm going on to problem 2, which is what's on the board here. So you see it's x to the 3/2 power, and you see the graph of it on the second sheet of paper, and I didn't repeat all of this that I had for problem 1, where it shows the curve and the differential arc length as a function and the arc length itself. So you can look at the picture that's on the top of the second sheet of paper in for a hint as to how this graph looks. So then you do your derivative, because you're going to take this formula and integrate it. And so 3/2 down in front, and the new exponent is 1 less. And then the squared derivative would be 9/4, square of the square root. So then your arc length is the square root of 1 plus the squared derivative. And then you see this is a U substitution problem, which is one reason that I'm doing it, because I wanted to review U substitution with you. It's one of those things where people always struggle with it somewhat until they've worked a lot of the problems. So if you're going to call all of this U, which is what I'm doing, then the first thing you want to do in a definite integral is get the new limits, so that when you rewrite with the letter U replacing whatever you called U, you are putting correct numbers on your integral sign, which go with the correct U values corresponding to the original X values. You see, it's mathematically wrong to rewrite this with a U to the 1/2 and the 4/9 du for the dx and use the old limits. It would be wrong if you wrote this and then still had 0 to 4. And you're tempted to do that if you don't actually find out what the new numbers should be. So if this is to be U and X is 0, then put 0 where you see the X, and that's the U you get. And in the same way, if X is to be 4, put the 4 there, and the 4's cancel, and then you have 1 and 9 making 10. So the new limits are 1 to 10. I'm calling this U, and then when this is U, the corresponding du is 9/4 X. So then you solve for the dx, which is 4/9 du, and replace. And so this is dx, this is U to the 1/2, correct limits. And now you know what to do. Add 1 and divide by the new exponent. So I factored the 4/9 out. Now I will add 1, get the new exponent, divide by that, put in my limits, and this is what the book says it is. I didn't get Maple to actually do the arc length, but if you were in Maple and had the problem and simply had typed arc length and then the curve and then the limits, Maple would have told you the answer. Okay, so now remember I started here and then I went over there and then I come back to number 21 and go on there. So we're going that way. Let's see, somebody got here didn't get the handout. Okay, yeah. I guess both of you guys. I think he needs one also. Oh, you got one. Anybody have one of these? No? Okay. So, going to this end. If you look at problem 3, for which I think there's a graph in your handout also, we have x as a function of y, as you see, x equals g of y. So I rewrote this. Here it was 1/4 times 1/y. I rewrote that with the negative exponent to do the derivative. So 3y squared over 3 cancel the 3's, and then minus y to the minus 2 over 4. And then you can rewrite like that. Now, this problem and several of the problems that are in that section are quite clever in that when you do 1 plus the squared derivative, as I'm doing here. What you will end up with is something which is actually a perfect square. Remember that your arc length formula wants you to do for your curve 1 plus the squared derivative and then square root the whole thing. So these are made so that the square root, if you do it right, will actually come out to be something you can work with. The square root sign will disappear because you'll be square rooting the perfect square. So watch how this goes. So you have your derivative here. So to square it, then you're taking this times itself, like FOIL, 2 terms by 2 terms. So if you think of it that way, the first times the first is the y4th, and then the outside would be this times that, so the y squares cancel, and then the inside would be this times that, and it's the same again, the y squares cancel, and then the last would be this times itself, which gives you plus, and 4 squared is 16, and y squared times itself is y4th. And then you're adding 1 to that, because that's in the arc length formula. When you're doing ds dy, it's 1 plus the square derivative that you take the square root of, and then you integrate that. Well, notice that when you add 1 to this, notice these two are minus a half, and you add 1, so you get plus a half. And this thing is this square. Again, if you take this and FOIL it out, this times itself, you'll see that this is what you get. That's pretty clever. But there are several problems of this type, so you want to look for it. That's why I'm going through it with you, so that you'll know to look for it. So what we end up with then, remember that this perfect square is this whole thing, 1 plus the dx dy square, and then you're going to square root that perfect square. So you're putting a square root sign on this, which I'm showing you here, and this is certainly positive, so the square, the square root of the square is supposed to be the absolute value, but when it's positive, it is its own absolute value, so you don't have to mess with absolute value signs. So then I rewrote the 1 over 4y squared with the minus 2. Drink some more water here. So then you know how to do the antiderivative. You add 1 and divide by the new exponent on both of these and put on your limits. So if you rewrite this to read a little better, you're taking this expression and evaluating at 3, and you take away the value of 1, which I've done here, and you end up with 9, just a little bit less than 9. 6 9s are 54 over. So this is 54 over 6 less 1/6, which you see comes out of these fractions here. So a fourth minus a third minus a 12th amounts to taking away a 6th, is what it amounts to. And so we'll look at the recipe box when we need the recipes. Meanwhile, take a look at problem 4, which I think also is drawn for you with the maple. You see the graph of 6.3 number 4 on the back side of the center sheet of paper, which is handout. And again, this is a function, x is a function of y. And the part of it that they're asking you to work with is the upper curve. You see, it's a sideways type of graph. It's a relation that goes to an extreme at the left of minus 2/3, I guess, and then it bends back. But we're looking on the upper part of it because they want the arc length when we finally get down here. For y going from 1 to 9, and y equals 1, as you can see in the maple picture, would be the level at which the curve is at its extreme left, looking at the picture, when you're going, measuring your arc length on that. So, we do the dx dy, so we have the 1/3 here, the 3/2, y to the 1/2, then the minus 1. Then here we want the derivative of the square root of y. And of course you can use the rule. You can take the 1/2 y to the minus 1/2, but I recommend memorizing this, or at least writing it down where you can find it, because you find so many problems where you want the derivative of the square root of something. And so I've set it up as a chain rule type thing where I have square root as an outside function and u as a function of x, say, as an inside function. And so the derivative of the square root is 1 over twice the square root of something, whatever it is. And then if it isn't just the same letter as this, the chain rule says you times what factor is here by the derivative of whatever is inside with respect to whatever letter is here. So this is my recipe box rule for the derivative of square root, which is this factor, and I have this as a chain rule, which you would get when these are different letters. Okay, so I encourage you to put that where you can find it, either in your head or somewhere. And so I've used that here to get from here to there. And then my dx dy simplified after the 3's cancel. You notice there's a 1/2 there and there, so I factored it. So I have square root minus 1 over square root. So then when I square that, my half becomes a 4th, and then I'm going to FOIL this out, multiplying it times itself. So it's the same kind of game again. Here's the 4th. This times itself is here. Then outside would be this one times that. And you see the square roots cancel. So you get minus 1. And then inside would be these two, and the square roots cancel. There's another minus 1. And then last would be this times that. So minus times minus is plus. Square root times square root is 11. And so is y minus 2 plus 1 over y. Then, if you add 1 to that square, you notice that when you carried this in here, this is a minus 2/4, and which is how I wrote it here. And you're adding 1, so that's going to give you plus 2/4 in the center. And then this is this perfect square of square root y plus 1 over square root y. My 1/4 here is common factor. So this right here is what this will give you if you take this and FOIL it out the same way that I did these. See, all you'd be doing is making these pluses, and so all that you're going to do is make a plus in the middle instead of a minus. So finally then, what the arc length formula wants, which is the square root of this, would be the square root here of a perfect square. And the square root of 1/4 would be the half. And then here you have your y to the half, and then I rewrote this with the negative exponent because I want to do the integral. So I add 1 and divide by the new exponents and put on my limits. And I work through all that and get to what the book has. Okay, any question on that? So then let's go on to the other section, 6.4. And if you notice, that's what's on the front of the last sheet of paper that you got. Surface of revolution around the horizontal axis of 2x minus x squared, square root of that. So that's what this is, square root of 2x minus x squared. And you can see what kind of looking thing you get. You take that curve and you rotate it around your x-axis from some starting point to some ending point on the x, and you get a kind of barrel-shaped surface. And then if you type surface of revolution in the student package and your curve and your limits, and you say output equal integral, number 3 should correspond to what we're going to get here at the board. And then if you just type surface of revolution and don't say output, you get what the surface area is, which is apparently 2 pi. And so you'll notice that that's finally where we get. So we're rotating this with these limits. And so notice that what we need for the surface area formula is 2 pi times the radius from the x-axis times the square root of 1 plus the squared derivative of our curve. This is our differential arc length again. So what we need to be able to do is the derivative of this with respect to x. And you see, this is the reason why I gave the chain rule version of the derivative of the square root of something, because that's really what we have. If you want to call this u right here, doing is the derivative of square root u, which is 1 over twice square root u, times by the du dx when u is different from x. So this right here is my recipe. So I have 1 over twice square root 2x minus x squared, because that's the curve. And then if you take the derivative of 2x minus x squared, you get 2. And then from here you get minus 2x. And so this is 1 over 2u, and this is du dx. And then what we can do, you notice the 2 here factors and cancels that 2. So our dy dx then is also the same as this. And then 1 plus the square derivative would be 1 plus this squared, which is what's down here, of square root. Then I get common denominator, and then as you see, a lot of things cancel out. The 2x does, and the x squared does. And so finally, you're ending up with 1 over 2x minus x squared. And so our formula for the surface area is 2 pi times the radius from the center axis. That's the x-axis, so the radius from the x-axis to the curve is the y value. And then this is our differential arc length. So this is our ds dx. And so what we have is that y, the curve, was the square root, 2x minus x squared. We found that this simplified, you see, to here, and so you have the square root of that. This is your square root of 1 plus the squared derivative, and then dx is over here. Well, now notice that this is the same that is, so this cancels with there, so you have the 2 pi and 1 and dx from a half to 3 halves, and that's how you get the 2 pi. So this problem, when you get all done with all this work in here, it all cancels out, which is kind of a happen-so, but it is, after all, the first problem in the group that I want you to work with on getting surface area. What you certainly should understand is that if you just think of all the curves that are out there and all the surfaces you can form, most of the time your integrals are not going to be something that you can do in the way that we're doing these, where you can get the antiderivative. Most of the time, to get a number, you would have to work with one of the schemes for numerical integration, where you can't get an exact antiderivative formula, but you can get a decimal answer. Now, how do you do that sort of thing? That's in chapter 8, so be patient and we'll get there, but we won't worry about it today. But I do point out that the homework problems in the book that I've asked you to do are carefully designed to be something that will work in the sense that I've been doing things. And that would be true with the My Math Lab problems as well. You'll get to an integral and you can't find some other function that your integrand is the derivative of. However, you can get if it's a definite integral, you will be able to get numerical approximations, as we'll see in chapter 8. Okay, so now let's look at 6.4, number 21, if you have your book, there's a picture of it in the book. And I'm assuming that either if you don't have a book here, you have it at home and you can look at the picture, so I didn't attempt to draw it. So what you're talking about is the surface area, the surface where you're taking x equal e to the y plus e to the minus y over 2, which, if you can think back to Math 170, is the same as cosh, the hyperbolic cosine of y. So you're taking the graph of cosh between the limits as given and rotating around the y-axis so that your radius for this surface of revolution is the cosh of y, and then they give you the limits on y, 0 to log 2. So our surface area is 2 pi radius, and then the differential arc length, where you're expressing the curve as a function of y. Okay. If you can remember Math 170, I think that it's chapters, I think it's section 7.4, although I might be wrong on the section, but it's in chapter 7 anyway of Thomas' book. The derivative of cosh is the hyperbolic sine, is sinh. So then your 1 plus dx dy square is 1 plus sinh square, and then there's an identity. 1 plus sinh square is cosh square. Remember that the hyperbolics act a lot like the regular trig functions, except that if you erase the h here, cosine square plus sine square is 1. If you put the h in, cosh square minus sinh square is 1. So they're very similar, but you get these sign changes. So anyway, this is the identity. So what you have then is your surface area is the 2 pi, the radius, then the differential arc length here. After you do this trig identity, 1 plus the derivative square becomes cosh square. And again, your cosh graph looks like this, so it's never negative. So the absolute value is just cosh. So you have cosh here and cosh here, so you have that square. So then the question is, how do you integrate cosh square? And there may be an identity there, but you don't have to worry about that. You can just rewrite it back to what it is. And so write out cosh y, which is e to the y plus e to the minus y over 2. And do it again because it's squared. So the 2 times the 2 is the 4. And then you have this times this. So then FOIL your numerator out. So you have e to the 2y first, and then outside e to the y, e to the minus y is e to the 0, which is 1. Then inside, another 1, and then last, e to the minus 2y over 4. Okay, so now we go over to here, and we have this integral from 0 to log 2. I took the 4 out in front, you see. So 2 pi over 4 is pi over 2. And so then integrating, that's another of the recipes, with something like e to the a times y. It is actually, you see, a u substitution problem, but with a problem like that, it's not worth doing u substitution all your life, just learn it. that it's your function back again divided by whatever is the coefficient. That same kind of thing is true with sine and cosine. You use those so much that you should just learn. And you have a similar one if this is sine, but I've run out of room to write it. So that's what I've done there. So I've taken the e to the 2y and said its antiderivative is e to the 2y over 2. Then the 2 gives me 2y, and then here I have my e function over minus 2, so I put this 2 here and the minus sign there. This could have been a plus here and a minus down here. It's the same thing. Thought this was easier to work with. So then we have our limits. They're log 2. And so I put log 2 there, and there, and there. And then at the lower limit, you see you can't just ignore that because e to the 0 is 1 after all. So you have e to the 0 over 2, and then 0, and then minus e to the 0. So it turns out these cancel, but that's a kind of a happen so. So what it leaves you is this to work with. And you have your general rule that a to the u is e to the u log a. That's true because the e function and the log function are each other's inverse functions. Before I forget, we better do this. So if you brought up the package that's student calculus 1, notice Maple is very, very picky, as computers are, of course. And so if you want it to work, you have to do just like a habit. So the student has a capital S, and the calculus 1, you notice, has a capital C, and there is no space between the S in calculus and the 1 there. I can remember at one time trying to get that to work, and I had a space there and it wouldn't do it. It's very annoying sometimes, but anyway. If you end with a colon, any Maple command either has to end with a colon or with a semicolon. If you end it with a colon, then the computer responds to the command, but it doesn't display. It just simply is there. If you end with a semicolon, then it displays, and what you get with the semicolon then is it lists all these different choices that you have in that package. And you see there's a great deal that you could get it to do, most of which we won't do anything with. But I just wanted you to see how powerful that program is. Anyway, if you type volume of revolution with due regard to a capital V, you notice, and a capital O, and a capital R, and then square root X, SQRT is square root of whatever, 0 to 2, output equals integral. What you're doing is taking the square root curve from 0 to 2 and rotating it around the x-axis. And if you do this, if you think of it as a disk method, for example, your radius is the square root, So your radius squared is square root squared, which is x. Pi times squared radius is the area of your disk, and times dx is the volume. So the integral, that's number 2 there, is actually a disk method then, a solution to it. And then same thing again, volume of revolution, output equals plot. You see the picture of the surface, the outer surface. Volume of revolution, output equals integral. Now this next one, you notice, is square root x square root 2. So that's a figure, you see, that's in between the two curves. You have square root x and from 0 to 2, and then square root 2 is a line. So that one is the picture that you see if you turn the page. If you want to see what that one is, turn the page, and you see in the green you have the cylinder centered on the x-axis, for which you have radius equal to square root 2, and then the inner one, which is in red, is the same figure that is on the first page, although all that you see is the end of it toward the origin. So as you see, it says up above the picture on the back of the sheet of paper, the volume of revolution around the horizontal axis between square root x and square root 2. So you can see then that it'll give you the integral, it'll give you the actual answer, volume of revolution. If you don't say output equals anything, it'll give you what the volume is. Output equals plot then is what draws the graph for you. And then the next, going down the page on the back side of the first sheet of paper, this time the axis is vertical. The formula number 5, volume of revolution square root x. See, before the axis was horizontal, but if you want to go around the y-axis, you type axis is vertical, and you have your integral. And this one was a shell method. If you look at number 5 and think about it, you have 2 pi times your radius, which is x, times your curve, which is square root x, and that's how you're getting 2 pi x to the 3 halves, x times x to the 1/2, you see. So that's actually a shell method integral. And then if you just want the volume, it's number 6 is telling you that. Then this next one, the volume of revolution around the vertical axis of x to the 1/2 power, the square root. So you have the square root for your top curve, and the bottom is your x-axis. So you can, if you like things like this, then I can recommend the Maple program to you, and you can play games with it. This is not, Maple is not anything that is required. But what I will do is I'll give you Maple handouts so you can see what a program of this sort can do. And I leave it up to you whether you want to get involved with it or not. Meanwhile, let's go over and talk about differentials a little bit. So, you should not be surprised that here comes another handout.